Okay, in this video we're going to look at another situation where we have a configuration of continuous charge distribution, and we're going to again try to see if we can calculate the magnitude of the electric field at some point away from this charge configuration. This will be a little bit more complicated. The calculation will be a little bit more complicated because we're going to think about a more sort of sophisticated arrangement of charge, and that's a ring of charge. So I'm going to try to draw this ring. So if we imagine right here we have some ring of uniform charge density. So here it is, and I'm sort of I'd like to imagine, for the sake of this argument, that the ring, the plane of the ring is entirely along a y-axis. So in other words, there's an x-axis running through here, through the center of the ring. This is an x-axis. And what I'd like to do is see if we could calculate the electric field at some point along this x-axis, let's say right there. So we could define this as, well, first of all, let's decide that our ring here has a radius capital R. That's the radius of the ring, big R. And we'll imagine that the point that we're interested in is a distance z away from the center of the ring. So this distance here from our point to the center of the ring is, we're just going to call that z. And mention that this is going to have a uniform charge density, which means it's a linear charge density again, so we'll call that lambda. And so the lambda is just going to be the amount of charge q, and so I'm going to also imagine that this ring has a positive charge q, and the charge density then would be q divided by L, where L is the circumference, the linear length around this ring. Okay, so let's think about this a little bit. Clearly, every little piece, there are an infinite number of pieces along this ring, and every little piece is going to contribute to the electric field at this point. The problem is every single point has a slightly different distance, slightly different value. So how are we going to sum this series of infinite points along the ring? And we're going to use the exact same tactic that we did in the previous video, which is to cut this ring up into an infinite number of teeny tiny elements dq, and then go ahead and take the integral of these different elements dq. So I select one point up here. I could have chosen any point along the ring, but I'm going to select a point right there that I'm going to call dq, and that little piece dq is going to contribute some infinitely tiny de along this line. So along this line right here, there's going to be some de right here. I'm imagining that the ring is positively charged, so I'm drawing the E vector arrow away from the ring. All right, so now we have to go ahead and think about how we're going to calculate the teeny tiny piece of electric field, or amount of electric field dE produced by this teeny tiny piece of the charged ring dq. And we're going to again use our equation for the electric field. So I'll say dE is going to be k dq over the distance squared. And right away we have to think about, what is our distance here? Well, the distance in this case is here, from dq to the point. That's our distance. And we'd like to express that distance in terms of r, the radius of the ring, and z, the distance from the point to the center of the ring. And since this is a right angle, I can use the Pythagorean Theorem and say that this right here is the square root of r squared plus z squared. Just the hypotenuse of this right triangle. So if that's my distance, if that's my r, essentially, if this is my little r that goes down here, and I'm going to square that value, then in the denominator I would just end up down here with an r squared plus z squared. Well, one thing I'd like to do here is recognize, and we did this in the last video, but we're going to do it again. If the charge density is q over L, I can write that in terms of these little infinitesimal pieces by saying that if this teeny tiny piece of the circle, piece of the ring, has a length ds, and that little piece ds carries a teeny tiny charge dq. So I could write the charge density as dq over ds. I choose S because S is our unit for arc length. So this is some little piece of the arc. So dq over ds, that is also equal to lambda. And so, of course, I can rewrite now. I can say that dq, another way of expressing dq, is to say lambda ds. So now I go ahead and I can write this, k lambda ds over r squared. Oh, that's very messy. Let me do that again. So another way of writing this is k lambda ds all divided by r squared plus z squared. All right, so we're getting there. We're doing some good work, but it may have occurred to you when we look at this picture, and this is one of the reasons this is a more elaborate configuration than the line of charge we did before. It may have occurred to you when you look at this picture that there are two pieces of dE. There's a component of dE. There's a component of this electric field vector that points parallel to the x-axis. I'm going to call that dEx. And there'd also be a component that's essentially pushing in the y direction. We could call that dEy. And it may be sort of, I don't know, intuitively obvious to you when you look at this that all of the dEy's from all of the tiny little dq's are all going to add up to 0. And to understand why that's the case, I selected a tiny piece dq up here, which is contributing an electric field vector along the negative y-axis. But there would also be a teeny tiny piece down here that would contribute, I'll do it in a different color so you don't confuse them. So there'd be a tiny little dq down here that would contribute a tiny little dE up here that would have a tiny little dEy all on the positive y-axis, which would cancel with the negative dEy here. And since this ring is symmetric, and the symmetry of this configuration is critical. If this were not a ring, if this were not something where there was a kind of axial symmetry, we couldn't make this argument. We couldn't simplify it, and it would be a much more difficult problem. In other words, if this were like some sort of irregular kind of continuous form, this would be difficult. But the fact that it's a ring, the fact that it's axially symmetric means that all of these y components are all going to cancel out, and so I can effectively ignore them. So I'm going to actually get rid of all those green arrows now so that you don't worry about them. So by symmetry, I can now go ahead and decide that I'm going to ignore all of these dEy's. And the only thing I'm interested in then, if you follow that argument, hopefully you do, the only thing I'm interested in are the x components of that electric field. And how do we determine that? Well, this x component is related to this angle right here, which I'm going to call theta. There's that angle theta. This is the same as this angle theta. These are vertical angles, so this is the same thing as this angle theta. And so dEx is just dE times the cosine of theta. So I can continue my calculation by saying I'm only interested in dEx, dE along the x-axis, and that's going to be k lambda ds over r squared plus z squared times the cosine of theta. So that's my equation for dE in the x direction. Now, it's going to be hard to integrate a theta value here. I've got cosine of theta, and I don't want to integrate it with respect to ds. They have different dimensions, so that's not going to work. But maybe I can express cosine theta in terms of a length, and I think you might be able to see that we can do that, recognizing that this is theta right here, and recognizing that theta is adjacent over hypotenuse. I can express cosine theta. I can recognize that the cosine theta is going to be z divided by z squared, r squared plus z squared to the power half, square root, right? So I took this over this, adjacent over hypotenuse. And that allows me to rewrite this, and I realize this is getting ugly, but I promise it will simplify. So we can now say dE in the x direction is k times lambda ds divided by r squared plus z squared times cosine theta, where cosine theta is this thing, times z divided by r squared plus z squared to the power half. All right, and how can I rewrite this? Well, I can multiply z on top. I get k lambda z ds over r squared plus z squared to the 1 plus 1/2, that's 3 halves. Okay, well, that's all well and good. I now have a satisfying expression for the x component of the electric field produced by this tiny element along the ring. But in order to calculate the entire electric field, E, this will be also along the x direction, I have to integrate all of these teeny tiny pieces. And I can do that now because all of my variables here are in terms of a length. So what am I going to do? Well, first of all, we ask ourselves, what in this whole expression, what's a constant and what's a variable? Well, k is a constant, we know that. The lambda, we started by saying it's a uniform charge density, that's a constant. Z is a constant, right? We picked a point, some fixed distance, and the radius of the ring doesn't change. So all of these are constants. So I can pull all of them out of the integral, and I can say k times lambda times z over r squared plus z squared to the power half, or power 3 halves rather, times the integral. Now what's the integral? From where to where is the integral? Because I'm integrating ds. Well, that's going to be the entire circumference. So from 0 to the circumference, which is 2 pi r. So I'm going to integrate from 0, s equals 0, to s equals the full circumference, 2 pi times big R. And I'm integrating simply ds from 0 to 2 pi r, which is really simple integral. I end up with the x component of the electric field is k times lambda. Actually, I'm going to write this. I'm just going to put the z in front of the lambda. K times z times lambda times 2 pi r. Right? It's 2 pi r minus 0 is just 2 pi r, all over r squared plus z squared to the power 3 halves. And we are kind of done, but I'd like to, there's one really nice little simplification we can make. What do I have here? Well, this is the charge density, that's the density of charge, multiplied by the entire length of the ring. Well, if I take the entire length of the ring, in other words, 2 pi r, that's L, right? That's the length of the ring. And we noted way back up here that the charge density we defined as Q divided by L. In other words, lambda times L is simply the entire charge Q. So this whole thing, lambda times L, is just the total charge on the ring Q. And that makes life a bit easier to simply say that the x component, the effective component, the only component of the electric field that matters, is just k times z times q, all divided by r squared plus z squared to the power 3 over 2. And that is our final result. Again, as I said in the previous video, this particular equation is not of overwhelming significance. You don't have to memorize it or anything, but the logic, the tactics that I used in generating this equation are important. So do not waste any of your time or effort committing this to memory. Just make sure that you understand the strategy. One last little, there's a quick way we can kind of double check this to see if it makes sense. What if we were a huge distance away from this ring? In other words, what if z were really, really big? So what if we were, like a mile away from this little ring? In other words, in this equation, what would happen if z is much, much bigger than the radius of the ring r? What would happen? Well, in terms of the equation, if z is some huge number and r is teeny tiny, then r squared plus z squared is essentially really just z squared. So then, if this is the case, then the equation starts to look like this. K times z times q divided by z squared to the power 3 over 2. Well, I've got a z up here, and I've got a z squared to the power 3 over 2. Well, what is that? That's z to the third. So this would just be, I'm going to get k z q over z to the third. The z cancels there, and I get k q over z squared. Well, that's interesting. What is this the equation for? Well, this is the equation for the electric field for a point charge. Right? That's our original equation. And that should make sense. That should tell us, aha, we've done something right. Because if you're really far away from this ring of charge, right? If you're like a mile away from this teeny tiny ring, from that distance, the ring itself looks like a point charge, or it should, because this minuscule distance r is irrelevant from some huge distance z. So that gives us some clue that we've done something right. Okay, good. That's two different continuous charge distributions down. We have one more to go in the next video.